Today we're going to be blurring the line between assessment and instruction, maybe assess for instruction. And the way I'm going to introduce this is, as a geologist, I want to show you this picture that I show my students. And I say, is there a fault in this image? So you're looking at it and you're thinking, well, maybe it's that crack over there, or who knows exactly what. Well, let me see if I can help you with some. I could give you the definition of a fault. A fault is a fracture in rock that shows evidence of movement or displacement parallel to the plane of the fracture. And if you're like most of my students, that doesn't help you at all. So you're staring at this picture. Let me try one more thing. Let me change the situation a little bit. Which image has the fault in it? And now hopefully you're spotting this layer here and you're seeing how, gosh, that looks like a crack, that looks like something's displaced. That is how you see a fault. And so in this particular situation here, was this task an example of assessment or of instruction? Did I just teach you how to recognize a fault? Or did I test to see whether you could recognize a fault? And the answer is, of course, you did a little bit of both. I was able to teach you something by just assessing you using the right prompt. And so what we learned from this is that there's this assessment concept and this instruction concept, and then there's a big overlapping area in between where you can do both of them at the same time. In EduSpeak, we call this formative assessment, but really it's about rethinking our instruction and assessment and finding the synergies between them. So that's what we're going to focus on right now. Now, I was one of the main writers on the California framework, including the chapter on assessment, which has on page 1305, assessment has two fundamental purposes, formative and summative. Now, I actually didn't write that particular section because I had written something else that ended up on the cutting room floor, and I'll tell you a little bit about why that. I had a whole section entitled Formative versus Summative Assessment, a false distinction. What I meant is that summative assessment is often thought of as this end point. But really, summative assessment should be used to adjust instruction just like formative ones, but maybe on a different time scale. So let's think about assessment. Assessment is part of a cycle, and I really want to emphasize that assessment is only useful if you actually use the results. So you might start with planning your learning goals and designing some assessments, and then you teach, and then you assess. Then the magic happens. Then you analyze and interpret your students' work, and hopefully use that evidence to guide instruction. This is what I was talking about, the different time scales that this can happen on. And we'll talk about that in a moment. Of course, you might end up revising your assessments to close the loop there, maybe even revising your learning goals as a result of this, and coming up with a complete classic view of the assessment cycle. But let's talk about the time scale of number 5 here, using evidence to guide instruction. You might say on the minute-by-minute level, oh, I'll have students discuss this more now because it looks like they're a little bit muddy on this point. Or I'll have them revisit their models again tomorrow. Or I'll add an extra activity next week. Or I'll revise my curriculum next year because this is not working. These are all different time scales that we can use assessments on. So assessment is only useful when someone actually uses the results. So here I have this question, who can use assessment results and what can they do with them? So go ahead and pause the video for a moment and think about those two questions. Here's some of the things that I came up with. I said administrators, they can allocate resources or make personnel decisions. Teachers, they can improve old lessons that didn't work or plan new lessons that target specific misconceptions that they've uncovered. And they know what to revisit or who to support. Parents can make school choice decisions or monitor their child's progress, be a part of that learning process. And students, this is one of the groups that I think is most overlooked in users of assessments. And if you look at the conceptual change literature and how to get people to revise their misconceptions, is the first thing they need to do is you need to confront them. The students need to be able to be aware of their misconceptions. And then in terms of growth mindset, we need to make them aware of their growth when they're changing and growing and learning new things. We want them to be able to see that progress so that they can internalize that as part of the learning cycle and really get value out of it. So we can do that. And lastly, assessment can actually help students solidify their learning. And we'll show you some pictures related to that a little bit later as well. Let's look at some specific examples of how assessment and instruction overlap. With this idea of timescales in mind, let's look at some specific examples of how assessment and instruction overlap. Beginning with this example I showed you with the two different rocks. You were actually being assessed on some prior knowledge that you had. The knowledge that rock layers form flat and that faults do something to break stuff. And that was the assessment component. But there was also something newly discovered that you had, where you gained further understanding of nature. That was where I was instructing you. I was teaching you about, in this particular case, that layers can be interrupted, and that's how you would identify a fault. And so this is an example where both of those things are happening at the same time. By its very nature, NGSS is best assessed in the context of new phenomena like we saw with those rock examples. And this is where performance tasks come in. They're described on page 1314 of the California Framework, and I've pulled out a list of criteria that we show on that page. The key is in the first bullet point, that performance tasks are supposed to present students novel phenomena or problems, things that they've never seen before, and they're going to apply their understanding in all three dimensions to try to explain those. What this means is that, by definition, you cannot teach to the test. Now, that's true of our statewide assessments, and it's true of the performance tasks that we're going to give in our classrooms. How does that work? Well, the clue's in the second bullet point. The performance tasks also provide instruction and context so that the students can understand the nature of new phenomena before they're actually asked to be assessed or apply their three-dimensional knowledge to understanding them. There's some other bullet points here. They include multiple tasks that focus on at least two dimensions, and performance tasks can be formative or summative, and the list goes on that page. Let's take a look at an example assessment, and this is derived from the Stanford NGSS Assessment Project, and you can see the link to their original source down here on the bottom. I've reformatted it a little bit for our screen, but they have three different objects that they've dropped here, and they want to know which graph best represents the kinetic energy of the objects. Use the mass and speed to help you decide. Now, first of all, is this a phenomenon that your students have necessarily done? Have they dropped these three balls before? Have they dropped any balls before? They may or may not have done this exact task before, and it's new to them. Take a moment, of course, to look at these four graphs and figure out which one is the correct answer. The key is, of course, to notice that the speeds are all the same, but the objects have different masses. So we start in the lower left and we say, these three here all have the same kinetic energy, but I know that kinetic energy depends on mass. Heavier objects seem to have more kinetic energy than lighter ones. So that rules out the bottom left. On the right here, that we start seeing a trend, but if we look at it, the one with the most kinetic energy is the lightest weight object. And we know that it should be the heavier object. And our top two graphs both show us examples of the heavier object having more kinetic energy. The question then becomes, is this a linear relationship, like shown on the left side here, or does it go up something more than linear? And we, of course, know that kinetic energy depends linearly on mass. So what we're doing is we're asking our students to apply all three of the dimensions. And here is the foundation box, where we're asking our students to apply their ability to analyze and interpret data. They needed to know how to read those graphs, and we were testing to see if they could. They needed to know that kinetic energy depends linearly on mass, and we were testing their ability or assessing their ability to apply that information. Lastly, although maybe it wasn't so explicit, was the cross-cutting concept, where we're looking at scale, proportion, and quantity. Our students need to be able to understand about proportional relationships, that sometimes they're linear and sometimes they have different forms of their relationship. And we could test to see whether or not students understood that. So that was an assessment. Now, this is, of course, is actually the type of task that you might have students do. So can you think about how this would work in the instructional domain? Well, you might tell your students, drop the following balls and compare the amount of damage that they do. And they would collect these data and come up with a kinetic energy graph like this. When we do this, we're asking our students to do just like they did in the assessment, where they are applying their ability to analyze and interpret data with the goal of learning that kinetic energy depends linearly on mass. And hopefully, in the process of doing that, they're also hitting on that cross-cutting concept that there are different types of proportional relationships. I would argue, though, that our students are not going to get that out of just doing this simple instruction task. They're not going to be able to see the linear relationship to high enough quality, especially if we're looking at a middle school item, which is what this is. Their data are going to be messy, and they aren't always going to be perfect, and they won't necessarily be able to notice that linear relationship unless, like we did with the fault, we show them a comparison. And that's where the assessment item comes in. In order for us to instruct our students and to get them to realize something, we might need to actually assess them and show them these graphs and have them look at the graphs on the top and say, ah, my data look more like the one on the left than they do the one on the right. And that helps me see that there's the difference between a linear relationship and a nonlinear relationship, and I'm actually learning something from doing the assessment that I wouldn't have gotten if I had just done the instructional activity by itself. Are you ready to try another one? Well, here's an assessment from, again, the SNAP project. And it shows us these rocks here and these layers, and it says that they're going to change over millions of years because of plate tectonics. They're going to be squeezed between two continental plates, and we want students to be able to describe what changes will happen. So we're starting with a sedimentary rock. We're going to have some energy that's going to cause some sort of process to happen where we're going to end up with still a sedimentary rock, then another process or change that's going to happen that's going to create a new type of rock. So what we're going to do is we're going to basically take items from this table here, and one item from this energy column is going to go into the diamond here. One item from the process is going to go into the first process arrow. Then we end up with a sedimentary rock. Then we're going to have another process that's going to go into this second process arrow, and a new type of rock that we need to select here. So our students are going to do that, and you can imagine this being done on a computer where they're dragging and dropping things into those items, or on paper. And then we're going to ask our students to write 1 or 2 sentences describing what their model shows. So I want you to take a moment to pause the video and give it a try, and then we'll discuss. The first thing we need to know is that this is a 7th grade performance task, and it involves energy from Earth's interior driving all of plate motion. So that's the easy part for us. The next part is what process takes our sedimentary rock and changes it some, but it's still called a sedimentary rock. This is not the process that's causing the sedimentary rock to form in the first place. This is a process that's taking our sedimentary rock and causing it to change a little bit. And so let's take a look at things. If the rock melts, it's no longer going to be a sedimentary rock. Could the rock increase in temperature or decrease in temperature? Perhaps from these energy from the Earth's interior. If it's energy that's added, then we're probably going to be increasing in temperature. If we're talking about squeezing, then we're going to be talking about increasing in pressure. Are we going to be breaking those sedimentary rocks? A sedimentary rock that gets broken is indeed still called a sedimentary rock. Are we going to deform those rocks? Possibly. Are the rocks going to get cemented together? Well, that's not what we're looking at in this particular case. That is how sedimentary rocks form, but we started with a sedimentary rock, so we are already cemented together, and that's not the process that changes a sedimentary rock into another sedimentary rock. Rocks that are compacted together, perhaps plates pushing together, plates pulling apart. So you can pick many of the options from here, and they are actually very valid. The energy from the Earth's interior causes an increase in pressure, where we still have a sedimentary rock, but if we continue to increase in pressure, so if we put more increase in pressure in here, eventually we're going to start causing some changes, and that rock will become a metamorphic rock. Or you could put, eventually the rock is going to melt, and if you put rock melt in this process box, then you're going to be changing into, I guess, a melted rock next, or perhaps an igneous rock after it cools. You can make an argument for each of those. But you can see this is a little bit challenging because our students are going to have to get used to the idea that there are many possible answers to this. And what you're going to have to do is describe them with your written text. What we were doing in this assessment task is we were assessing our students' ability to develop a model. And that model was also assessing their understanding of the flow of energy that causes the cycling of rock matter in Earth's interior. And I'm not so sure, this did not do a good job of assessing the cross-cutting concepts, in my opinion. Maybe stability and change, where we're looking at changes in rocks, maybe the flow of energy and matter, but it wasn't really a main focus of this particular assessment, in my opinion. But what was happening here is that there were both elements of assessment and instruction. If I had just given you this model by itself here, the blank spots, without any other things, that would be different than what I gave you. I actually gave you this table here that shows a whole list of possible processes, possible energy sources, and you had to think about each one, and in the process of doing that, you might be applying some of your prior knowledge, but it might dawn on you. You might realize some of the things that you hadn't realized before. And that's what happens when I show this assessment to a lot of teachers that aren't so familiar with earth science. What we've given them is we've given them a template or a menu of all the different processes that can happen to rocks. In other words, we've been teaching them about these different things. Can you think of an activity in the instructional domain that complements this assessment, where we explore these different processes in more detail? Well, here's a classic one where you can use crayons to model each one of these changes, each one of these processes that are occurring. You can take a cheese grater and break up rocks, then put them and squish them together to make those sediments into a sedimentary rock. You can add heat to represent the changes from metamorphism, which are slight changes, or you can get the rock so hot that it melts and it completely melts into a new form of rock, an igneous rock when it cools. And we could basically give our students this blank model here and ask them to fill it in as they were conducting this instructional activity. In that case, we'd still be assessing their ability to apply this science process of developing and using models. We'd, though, be learning that the flow of energy causes the cycling of rock matter in Earth's interior. That's the focus there. And our cross-cutting concept still will have to be accentuated. Perhaps it's a little bit more obvious when you do this activity by hand that this is about the conservation of matter, where we're looking at the same material moving through many different processes. Now that we've looked at a couple of examples, I want to go back and look at Chapter 9 of the California Framework, the assessment chapter, and look at how it's organized. It's organized by science and engineering practice. But wait, I hear you cry. Aren't performance tasks supposed to be three-dimensional? So how do we get away with organizing it based upon SEP? Well, it goes back to the purpose of assessment. It's to use evidence to guide instruction. What sort of evidence can we collect? Well, that's what students say, do, make, or write. Now, if you're looking at that and you're seeing do, when the domain of do is the domain of the science and engineering practices. This is what they're actually going to go about embarking upon that's going to allow us to collect the evidence we need. And if you're used to that word evidence and NGSS, the first thing you might think of is the evidence statements. And these are very useful resources for designing assessments and instruction. And let me show you how they're organized. They look like this when you download them off of the Achieve website. They've got the PE at the top, the foundation box, just like in our standards. But the thing that happens is that's magic is down here below. In this gray box are the actual evidence statements, the observable features of the student performance. And let's zoom in on those. This is a middle school physical science performance expectation, so let's look at it. It's construct, use, and present arguments to support the claim that when kinetic energy of an object changes, energy is transferred to or from the object. Now, hopefully, if you've been looking at NGSS PEs, you know that they are constructed by stringing together the three NGSS dimensions, including the SEPs. So which SEP are we using in this one? Well, oh gosh, there's the word argument and claim. We're looking at using arguments from evidence in this particular case. Well, the NGSS evidence statements are organized around SEP just like our chapter is, because this is the observable features that we can have. So let's take a look for some evidence in that practice. Well, there's the claims, the evidence, and the reasoning. Now, these, of course, evidence statements are three-dimensional, but they just have the structure of the SEP. Let's see if we can find some of the other dimensions in here. Well, the kinetic energy of an object changing and energy transfer, that's the disciplinary core idea about energy. And here we're looking at energy conservation and energy transfer. That's cross-cutting concept number 5, energy and matter. We'll try another one from middle school life science. Develop and use a model to describe the function of a cell as a whole and ways that parts of a cell contribute to the function. Again, it's pretty obvious which SEP we're looking at for this performance expectation. That's develop and use models. So how does the evidence statement tell us what are the things we need to be looking for there? Well, we should be looking for the components of the model, the relationships between those components, and then lastly, this, unfortunately, I feel like this is a terribly misnamed thing here. The last part in these evidence statements is called connections, which really is what can you explain using your model? What are the connections to the real world or the applications that you can do? And unfortunately, I feel like connections and relationships are too similar a word, but there's a reason from the research literature why these two words were used to be consistent with that research. But in your mind, you can see the components of the model, the relationships between those components, and then the applications of that model. And again, this is three-dimensional here. We've got nucleus, chloroplast, cell wall, all those great DCIs from the life science realm, and functions of a cell, and that's in there as the DCI realm. But also, the plants use cell walls to provide structure to the plant. That's structure and function, the cross-cutting concept that we're looking for in this here. And so, again, the evidence statements, as you look through them, each one of them, spot the practice, and you'll see the organizing scheme here is the SEP, which really helps us understand what the SEPs look like and what are the components of a good explanation, what are the components of a good question. And the evidence statements will help us understand the SEPs better as we look at the templates that are used by the evidence statements. Performance tasks can both collect evidence and strengthen 3D understanding. They are supposed to be here in the center part of our assessment instruction boundaries. So let me give you an example here from another SNAP assessment. And this is a longer performance task. The ones I showed before were both short individual items. But this is here a story about some kangaroos and an ecosystem. And I want you to actually download this yourself and take 10 minutes or so to work through it on your own. And then we'll come back and we'll discuss it. The short summary of the activity is that we're going to be developing a model over the course of this whole performance task that gets more and more sophisticated. It's going to start with some non-living things, then it's going to talk about how non-living things interact with the living things in the ecosystem, then we're going to change the ecosystem by adding a whole bunch of rabbits and add those to our model, and talk about why do we think that plants can't survive after the rabbits are introduced in the ecosystem. We're going to be looking at a disease that disrupts the rabbit population, and we're going to be having the rabbits die, and so we need to add some decomposers to our ecosystem model, and then describe how is it that this ecosystem would not survive without the decomposers. How are they doing things? What are they doing? So which dimensions were assessed in this task? Let's put this box up here. What were you applying or assessing, or was there some learning going on? Well, one of the things that I think is brilliant about this particular assessment is how it treats the science and engineering practice, which is, of course, in this case, developing and using models. Reflect on how this assessment really helped you scaffold or better understand how to develop the model. It built it up bit by bit in the assessment, which is actually a great way to introduce and instruct about how to develop and use models. So I'm showing that even if you had a good understanding of this system here, and you had an okay understanding of developing using models, going through this performance task might actually solidify your learning about how you construct a model, might help you sort of make some abstractions about that that would help you make models in the future. The same is true of the disciplinary core ideas. You might have a good idea of how matter cycles between all the different components in an ecosystem, but as you were discussing this performance task with some other students in the class, you might be able to solidify certain things. And what's happening here is that much like many assessments, as we're asked to recall information, that helps solidify learning pathways in our brain. I use this picture here of this well-worn pathway, is that the more you walk on the path, the more solid this path gets. And the same is true with learning that happens in our brains. As we assess our students on things, they're going to be forced to try to remember stuff, which is going to help solidify the stuff that they're trying to remember. And this is sort of the neuroscience basis for my statement that assessment and instruction are blurred. Let's look at another assessment. Now this one's not quite as refined. This is one that I produced, but it starts off in 1900 in Pittsburgh, Pennsylvania, where you had one of the highest rates of death and sickness and disease in the entire US. It was very common for people to die of a disease called typhoid. And I don't know about you, but I don't know anybody that's died of typhoid anytime recently, yet there was a time here in California in Sacramento where some large portion, like 30% of the city of Sacramento, was all wiped out in a single year from typhoid, and it caused that many deaths back then, and we haven't heard of it today. So what's going on? There's some real learning that can be happening in this performance task, but our job is to look at Pittsburgh and to track down why Pittsburgh residents were getting this disease so often. My first question for you is, we're going to begin this investigation by asking a question. So which of the questions below will be most useful to help you plan a specific investigation that might determine the cause of the disease? And I've given you 4 options here. And what I want you to do is be able to answer not just which of these questions you think is the most productive scientifically, but why you wouldn't choose each of the others. As you're going through it, you might say, all right, well, why are people dying so often in the city? That's a great question. That's our fundamental question. But the thing is, it's kind of vague, and it doesn't really get us any closer to answering it. That was the question that I started off in the beginning, the reason we started this. The next one, where in the city are people getting sick the most? Well, if you have some idea of where they're getting sick, you might be able to figure out what's causing them to get sick. So that could be a candidate. Are family members scared when someone gets sick? Well, that's really not in the realm of science in determining the cause. That's more about the effects of things. And then how many people die of typhoid in a typical year? In this particular case, a typical year is not really the one we're interested in. We're interested in finding out the causes, and this is not going to get us too close to the answer that we're looking for. So we have a selection here that option B seems like it's our best question. But again, as asking you those questions, I showed you a comparison of 4 different questions. And just like we showed the comparison and the fault at the beginning, those comparisons are going to help solidify our understanding of what makes a good question. Next, let's figure out here, now that we've got this question and we figured out where people are getting sick, let's look at some answers. Well, you collect data and show that people who live near the Allegheny River and rely on it as a water source are dying of typhoid at a higher rate than people who live in the mountains. So I'd like you to draw a system diagram that illustrates one way that pollution could get into the river and affect people. And so like many different system model computer program, you might drag these different words onto your system model and use some arrows to show the relationships between them. So go ahead and do that on a piece of paper in front of you, and let's see what you've come up with. Like many of our assessment tasks, what brings them into the instructional domain is when we bring in that comparison between different student responses. So here are 2, and I want you to notice what differences you see between them. On the left side, we've got rain and flowing in, picking up pollution and flowing into the river, and that affects the people. On the left side, we have rain flowing into the river, and we also have pollution flowing into the river, and the people are going to be drinking the river, but also producing some of the pollution. So there's a couple things on here. You might notice that the one on the right is a little bit more interconnected, a richer web of interactions. Seeing the model on the right might instruct the student on the left, might get them to think about how they could make their model more richer by basically drawing an arrow connecting people to pollution to help illustrate that important interaction that's missing from their diagram. So by assessing them, we can help instruct them on that key thing and solidify some learning. The other thing, though, is that both of these models present valid ways for pollution to get into the river, but they're different ways. One of them is basically pollution being picked up by runoff, and the other one is direct pollution going into the river. These 2 assessment results side by side allows us to instruct our students in these 2 different pathways within the water cycle and really emphasize the differences between them. It turns out that the model on the right is a little bit more representative of what was actually happening in Pittsburgh around 1900. What they had was that they had just invented a new sewer system. They had been able to take their sludge and send it away from the city. A great thing, a great boon for their local community. What do you do with sewage? Well, at the time, they figured, let's just get rid of it. Let's dump it in the river. And they did that, and the outflow from that sewage system was just upstream from the city's water supply. And at the time, they were just developing ideas of germ theory, and they hadn't quite realized how much of a problem that would be, something that we now have a better understanding of. They were slowly understanding that maybe people were getting sick from the water, and so what they started doing is they started filtering the river water supply through sand and gravel, and that cleaned it and helped prevent illness. So can you look at this graph below and figure out which year did they probably begin filtering the water? This particular assessment is assessing your ability to apply your analyzing data and interpreting data skills. So let's take a look at it here, and hopefully you see that the amount of deaths from typhoid dropped very suddenly around 1908 and a little bit more in 1909. And in fact, those are the 2 years that they worked on the first stage of the water system completing in 1908 and the second stage finishing by 1909. And you can really see the effects here. And this is a wonderful teachable opportunity here by doing this simple data analysis activity, really emphasizing how important it is, our understanding of germ theory and understanding how our water must be clean. This is a fantastic way for us to emphasize California's environmental principles and concepts as an instructional piece, but it's disguised as an assessment. As I said, I put a lot of time and effort into the framework, but there's one thing I did not do. I was not involved in selecting the clip art that they used throughout the framework to decorate it. And I want to end by looking at this picture. This is the front page of Chapter 9, where they have this teacher doing assessment, it looks like. And I want to ask the question, what's wrong with this picture? In my head, you should be thinking of assessment more like this picture, with the teacher and the students actively involved in learning from the results of the assessment. And this is a much richer picture of what assessment should look like, where there's a blurred line between assessment and instruction.